So on a recent afternoon, we went out to the train yard and got on a train and went for a ride. I don't particularly like this problem because I went through and did this problem and checked it with the answer, and we disagree a little bit, and that's because apparently we're just starting with the train at half an hour. I guess we're just ignoring the fact that the train had to start somewhere. I don't know. Anyway, so what we're going to do is we're going to look at this problem per their restraints. I might modify it a little bit. After train has traveled a half an hour, it increases its speed and travels at a constant rate for 1.5 hours. Complete parts A and B below. Don't worry about A and B. I will give those to you. So traveling, and I don't know, the person inside the train is shouting out, traveling at a speed of 30 miles an hour up to 45 miles an hour. Okay, so first of all, we want to look at our domain. And our domain, are we looking at time or speed? Well, usually, because what is it that, when does the train change? The speed depends on how long it's been traveling. So after half an hour, it increases its speed. So it depends on how long it's been traveling. So our domain is going to be our x always, but it's going to be our time for this one. And so our domain is going to be our time, and it's going to include that half hour starting spot, and it's going to go until what? And it travels at a constant rate for 1.5 hours. We might be tempted to put 1.5 hours in here, but really we started at a half an hour plus the 1.5 hours, so it's going to be 2. I would dare argue that this should start at 0 because the train had to start at 0, and also the speed had to start at 0, but we're ignoring that so that we can have a weird domain. Okay, now the speed, how about our range? The speed is the range, and what would that look like? Well, because the train says so, or whoever's inside the train shouting really loudly says so, it travels at a speed of 30 miles an hour to 45 miles an hour. So our range, it can go 30 miles an hour, so we have a square bracket, 30 miles per hour. This is in hours. This is in hours. 30 miles per hour. And then it goes all the way up to 45 miles per hour. And can it go 32 miles an hour? Sure. Can it go 45 miles an hour? Sure. Can it go 45.1 miles per hour? No. So the cutoff is 45 miles an hour. It can be anywhere in between. Okay, so the last part for this problem that isn't shown here is it asks us, how would we best represent this? We could do a table, right? We could do a table, but what would that look like? So we would have x for our time, y for our speed, and then our values would be what? So at 1/2, it was going 30 miles an hour. What about at, and we know 2, it was going 45 miles an hour, I guess. But what about in between? Well, we don't really know necessarily how fast it was going in between. So a table, this isn't discrete, so a table is probably not the best representation. On the other hand, a graph would be a pretty good representation. We could start here at, this is a half hour because we don't have 0. So it starts at a half hour and it's going to go all the way to 2 hours. Right here is going to be 30 miles per hour, and then, sorry, that's going to be 45 miles an hour, and then down here is going to be 2 hours. Okay, so at half an hour, it's going 30 miles an hour, and then it increases its speed. So at any point, we could figure out how fast it's going, right? And it could be a fraction or a decimal, and that's fine. I mean, at 30 miles an hour is half. So we want something that's going to represent a continuous slope, a continuous line, where in a table, we can't really get that. So this would be the best representation for this problem.